So deadlocks are the worst that could happen when you're using threads. But can we write a program that is deadlock free? Is there some kind of pattern that will ensure that a program never go into deadlock state? In this video, with hands-on examples, we will understand what deadlocks are, what happens when your program hits a deadlock, and how to write deadlock-free code. So here I'm using a cloud-based IDE called Replit to code this out. Because it is cloud-based, I do not have to set up anything locally, and I just need a browser to get started. Replit has an amazing LLM assistant named Ghostwriter, which is extremely powerful because it is vertically trained on programming and software development knowledge base. And the best part is it spits out answers and suggestions in the context of the code that you are writing. Apart from this, Replit has something called as bounties, which can help you make some money on the side. As a bounty, companies post paid projects on web applications, AI tools, Discord bots, and so much more. You can pick the one that interests you, complete it, and get paid. Just sign up on Replit with my link in the description down below. Once you sign up, on the home page itself, you can see a section called bounties. When you click on explore, you can see the projects that are listed there and the amount of money you can make out of that. Pick the one that interests you, apply for it, and just get started. So the link for the sign up is in the description down below. Go through that, sign up from my link, and this, to be honest, is a great way to make some money on the side doing what you love. So do check that out. So now let's head back to the video. So the most common side effect of multi-thread programs are deadlock. Let's understand it with a very simple example. Let's say we have 3 threads, T1, T2, T3. Each thread wants 2 resources to move forward and it wants exclusive lock on them. Which means that let's say T1 holds the lock on R1 but wants lock on R2. T2 holds the lock on R2, wants a lock on R3. T3 holds the lock on R3 but wants a lock on R1. Now this is a classic case where you can see a very nice circular dependency being formed and none of the thread could proceed because everyone is waiting on other thread to release the lock. This is where your program enters a deadlock state. What happens when a program hits a deadlock? Your program hangs and there is no, elegant way or a graceful way to come out of it. So, which is why deadlocks are deadly, and if you're writing a multi-thread program, you have to ensure that the program never ever enters a deadlock state. Because if it enters a deadlock state, you would have to either kill the thread, kill the process, reboot the system and whatnot to get out of it. So in real world, 2 very common examples, and we will look at them in depth, but just to give you a high brief of it, that databases ensures that it never enters a deadlock state. Now just imagine a database which obviously is multi-threaded. It handles so much of traffic in parallel, leverages all the cores, needs threads to do it. And if a transaction has logged a particular row and is dependent on another row which is logged by some other transaction, there is a circular dependency being formed. The database entering into deadlock state, there is no way for you to get out of it, which means either you kill one of the existing transaction, leads to poor user experience, or you reboot your entire database. Right? Either way, it's not a good experience and it would lead to a production outage. Similar case would happen when you're using web servers, because your web servers are multi-threaded. There is a chance of deadlock there. So your web servers ensure that they never go in a deadlock state. Plus, the business logic that you're writing as part of your API logic, that also, if you are leveraging multiple threads due to any reason, ensure that it never enters a deadlock state. Because everyone loves stable softwares, although boring, but yeah, like no one loves thrill in production. Right? So can we simulate deadlock locally? It should not be difficult, because then it just requires threads and you can mimic a lot of stuff there. So what do? Is we would try to mimic deadlock locally, and what we will see is what happens when your program enters a deadlock, and then we try to fix it. We will try to write a deadlock free code. Right? So to mimic this locally, what we do is we create 6 threads, right? And we would try to acquire lock on 3 records. So imagine this is a database. 6 threads are 6 transactions that are trying to acquire lock on 3 records, which is 3 rows. And when they try to acquire a lock on 3 rows, let's say they are trying to acquire lock in random order. Depending on the SQL query that is fired, it could be in some particular case, but let's assume we do it in random order, because at the end we care of simulating the deadlock and not like actually replicating it. Okay? So here, what our logic would be is our threads would constantly try to acquire lock on any two of these items. Will sleep for a couple of seconds, mimicking like some kind of processing, right? And then they would release the lock, right? Now here, because we have 6 threads which are trying to acquire lock on 2 records, it is possible that a deadlock is formed. For example, if you look at this diagram, here you can see how a deadlock is getting formed, right? And we would want to see what happens when the program hits the deadlock. So let's take an example. Let's take a practical hands-on example to understand how to, solve this, or how to see what happens when your program enters a deadlock. So here I'm using Replit, as you may see, because why basically set up things locally. So here, this is a simple C program in which what we are doing is we are spinning up threads. I'll start walking you through on what we are doing so that we understand what would happen when a program hits a deadlock. So here we are mimicking 3 records and 6 connections. 6 connections implies 6 transactions. There is a struct which mimics a record data having 3 attributes, like imagine it being name, 3 integers, so ID, age, and something else. Then let's say you have your struct in which you are storing record data and a log. We'll come to that. Now what we would want to do is when we are initting or when we are starting our execution, here our main starts over here, we seed our random function, we initialize database, add some dummy values into that. But the idea is that what we want is we want to simulate 6 transactions. So for I equal to 0, I is less than numcon, I plus plus. I'm spinning up a transaction. I'm just creating a string so that I can show it in a beautiful way. But the core idea is I'm just creating a thread which would execute this function mimic load and as this particular transaction. So 0 is A, 1 is B, and 2 is C, something like that. Right? Then what we are doing is this mimic load function, will take a look at it. But the idea is that when my threads are running, I would wait for all the threads to complete and then I'm destroying my mutexes. Now let's look at what mimic load does. Now what mimic load does, it is, imagine it's a connection or that is constantly trying to acquire lock on 2 random items. So here I invoke random function twice, record 1, record 2. And I would just, if record 1 is same as record 2, because we want 2 distinct records on which we can take lock. So I'm just acquiring 2 records at random. If they are same, we would just continue. But it's just a simulation, right? So here at this stage, we would have 2 records that this transaction has picked up, not yet acquired the lock, which are distinct. And then we acquire the lock on the records, rec1 and rec2 on this corresponding transaction. So we are passing transaction name as an argument. Here we are passing transaction name as an argument. Sorry, not here. Mimic load, transaction null, and here we are passing. Yeah, this is the argument that we are passing, which is txn. And this argument will be accepted over here, which is a char star, and we are just using it to print it. Right? So what acquire lock does is what we have is for each of the record, here you can see for each of the record, we have a record data in which we can store the 3 attributes that we just described, ID, let's say ID, age, and class name or class number. You could have strings and whatnot here. But along with that, for each record, we have a mutex, right? That is this logged or not, right? So what our acquire lock function would do is it would say that, hey, this transaction is acquiring a lock on this particular record. So that's what we would do. pthread mutex lock db of records of record ID. So for that record, I'm invoking a lock function. I'm locking that particular thing in this for this particular thread, right? And release simply just unlocks that particular stuff, right? That's what we are doing. So here, the idea is we take 2 distinct random records and then we acquire the lock on first record, acquire the lock on second record. It would move forward only when both of the acquisitions are successful. Otherwise, it would wait and then sleep for 2 seconds. It's basically mimicking some kind of processing, some kind of compute. And then we are releasing the lock, release lock record 2 and release lock record 1. And then we sleep. And this is an infinite loop that is continuously running. Imagine it's like continuously trying to acquire the 2 lock, process on that, release the lock, and so on and so forth. Right? Now, when we try to run this program, let's see what happens. When I try to run this, we see some print statements happening. We see transaction F acquired lock on record 1, transaction F wants to acquire lock on record 2, transaction A release the lock, transaction A release the lock on record 2, and so on and so forth. But now if you look carefully, our program is not moving forward. It printed a bunch of statements, but the program is not moving forward. Why? Because the program entered a deadlock. That if you plot a dependency graph of these logs, you would see that there would be a cyclic dependency that is formed. Because of which your program has entered a deadlock state and the program is not moving forward. This is what happens if your database enters a deadlock state. Right? So I'll stop this execution because now we have to fix it. But now we understand why our program would enter a deadlock and how and what would happen if a program enters a deadlock. Right? So now let's take a step to see how we could fix it. To fix a deadlock, you can very clearly see there is a circular dependency which you have to break. What are the possible ways to break it? You kill one of the thread and break a circular dependency. That's the easiest one. Now, which one to break? You can pick the oldest one, you can pick the newest one, you can pick the one which is least busy, pick the one which is most busy, depending on multiple strategies. Pick one that works for you, or just pick one at random and kill it. Right? And there is no one way to do it, to be honest. Depending on the system that you are building or system that you are using, they would pick one over other because depends on what suits them. Right? The second thing is, screw it, let me restart the process. If threads are causing it, let me restart the process. If multiple threads or multiple processes are in deadlock, you restart your system. The idea is you do restart so that the circular dependency now literally does not exist. Right? Two common ways of handling deadlock, but yeah, you pick the one that you write. Right? Now this is about when you entered a deadlock and then you're fixing it. But there are other ways to do it. Can we do better? What if we prevent a deadlock from happening? Now, most real world systems, they cannot afford to enter a deadlock state because they cannot afford that your program suddenly stops working. Let's say, imagine your database suddenly stopped working. Imagine your web server suddenly stopped working. Real world systems would want that their program, no matter what, no matter how extreme the situation is, no matter how rare the use case is, the program should never enter a deadlock state. So, is there a way to prevent a deadlock? So, few examples. This is where what you do is before acquiring the lock, most of your real world systems, they check the resource allocation graph. What we just saw, that dependency thing, that's a resource allocation graph, that which resource is allocated to which thread. So what happens is, whenever any thread or any process or any entity in your system has acquired a lock on something else, it maintains a global resource allocation graph for it. And before acquiration, it checks that, hey, if I take this, will there be a circular dependency that is forming? So this is deadlock detection, that is not really detection, but rather this is deadlock avoidance that is continuously running. Right? So here you are preventing the deadlock from happening by checking every time before you acquire the lock that, hey, if I acquire this lock, will it form a circular dependency or not? That's the core idea. Most real world databases do this. For example, in MySQL, if you try to mimic if you take exclusive locks on rows and try to mimic this deadlock, you would see that the second transaction, when it tries to acquire the lock and your database, it sees that if I give this transaction lock on this particular row, my database will enter into a deadlock state. It would stop. It would kill the transaction. The idea being that your deadlock is prevented. It's not avoided, it's prevented. That your system could have gone into a deadlock state, but you are preventing it because before acquiring the lock, you are always checking that, hey, would it result in a deadlock or not? And most real world systems prefer this. But there's another way. What if you completely avoid a deadlock? That no matter, like, there is no need of maintaining resource allocation graph. There is no need of checking cyclic dependency every time. Is there a way for you to write a code that will avoid the deadlock totally? And which is how you write a deadlock free code. I'll show you one of the examples to do it. And the example is really interesting. Thinking from the first principles, the program enters into a deadlock state because of a cyclic dependency that is formed, right? And the cyclic dependency is formed because, let's say I take example of two threads and two resources. Thread T1 has the lock on T1, wants lock on T2. T2 has the lock on R2, wants the lock on R1. Right? Now, because of this out of order acquiration, you see this deadlock condition, this deadlock situation being happening. Why? Because if they would have, if there was no way for your thread T2 to have acquired lock on R2, then your program would have never entered into a deadlock state. So that's the idea. So what if there is a total order in your system? What is total ordering? That if a thread wants to acquire a lock on two resources, what if there is a total order in which it would need to acquire the lock? So for example, let's say the total ordering that we do is numerically sorted, R1, R2, R3, R4. So if let's say thread T1 wants to acquire a lock on resource R1 and R2, it will have to acquire lock in the same order, R1 and R2. If T2 wants to acquire the lock on R2 and R1, so no, there's total order. T2 would have to acquire lock on R1 and then R2. So you are imposing a total order in your system where your threads would have to acquire the lock in a certain order. And this will help you avoid the deadlock. How come? Because, for example, in this case, the situation where T1 and T2 acquiring the cross acquiring the lock would never happen. Why? Because T1 will also acquire lock on first on R1, then on R2. T2 will also try to acquire lock on first on R1, then on R2. So if out of T1 and T2, any one of them, let's say T1 has acquired a lock on R1, T2 would not be able to move forward because it is acquiring the lock on R1, then on R2. This is the importance of total ordering. That in this situation, your T2 will have to wait until your T1 releases the lock that it took on R1. Why? Because there is a total order imposition that has just happened. This is how you avoid a deadlock, right? And this total order that you are imposing ensures that the acquiration is happening in order, which means that there is no way it is possible for your system to go for your T2 thread to acquire lock on R2 and then on R1. So R2 will always be free for T1 to acquire because T1 has acquired lock on R1. This total order imposition is one of the ways, not the only way, one of the ways to avoid a deadlock. And now let's see a quick demonstration of this. If we take this exact same example that we did, we just add one condition to it. We go back to the screen. Now here in the transaction or in the mimic load function, when we had this infinite loop trying to acquire lock on randomly picking record 1 and record 2, here there is no total order. Now here it is possible that your record 1 and record 2 could be R2 and then R1, in some cases R1 and R2, because we are randomly picking. So what if we impose total order? Something like this. What if we say that if record 1 is greater than record 2, we swap it and we swap it. So we say that swap the records if record 1 is greater than record 2. This means that by any chance if it was R2 and R1, it would be swapped with R1 and R2. This is imposition of total order in your system. And now if we run it, we would see that our program never stops or never hangs. It would continuously be moving forward no matter what happens. Because in case there is one of the thread who has acquired a lock on someone, there is in one order only the locks can be acquired on the resources. Right? This way what would happen is that there is never going to be a case where someone else has acquired lock on some other thing and then wants to acquire lock on something else. That's never going to happen. And this is one way. And it's not that every system can afford to put or impose a total order in their system. For example, in case of database transition, it is really difficult. But wherever possible, if you can impose a total order of acquiration, That would be the best way to write deadlock free code. And this is one of the ways. There are many ways to do it. This is one of the ways to do it. And this is pretty fascinating. And look how easy it is to mimic this thing locally to build a deeper understanding. Right? And this is how you write a deadlock free code. Right? One of the ways to write deadlock free code. And yeah, this is all what I wanted to cover in this one. I hope you found it interesting, and I would highly recommend you to just code it. It's not difficult. And by the way, it's not just C specific. You could pick literally any language to do it. You just need mutexes to mimic this. But once you get a deeper understanding on why it is working, how it is doing, you'll understand what database must be doing internally. And this is not what most databases do, but you will start framing the ideas around it. Right? So this is one of the ways to write deadlock free code. I'll cover a bunch more in future videos. But yeah, I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks a ton.